Hello everyone. In this video, we see about the linear differential equations with the constant coefficients. We know that an equation is said to be differential equation if it contains the derivative term. Suppose if we have an equation dy by dx plus 2d square y by dx square plus 5 equal to 0, then we can say that the operator d by dx as capital D and y is the dependent variable, x is the independent variable. So dy by dx means a change of y with respect to x. Now we are going to see the linear differential equations with constant coefficients. Consider a linear equation of second order with constant coefficient as equation 1. Here a, b, c are constants and capital X is a function of small x. Let us consider one without the second number, that is equal to 0, that is a into d square y by dx square plus b dy by dx plus cy equal to 0. Now the solution of this equation 2 is called the complementary function of 1. To solve 2, assume a trial solution y equal to e power mx for some value of m. Now we take dy by dx equal to m into e power x and d square y by dx square is m square into e power mx. So substituting these values in the equation 2, we get e power mx into a m square plus bm into e power mx plus c into e power mx equal to 0. So here e power mx is a common term, so we can take that outside and we can write that as equation 3. Hence m satisfies the equation a m square plus bm plus c equal to 0. This equation m is called, the equation in m is called the auxiliary equation. So after that, for finding the solution of the homogeneous case, we have the three cases. So first case is, let us consider the auxiliary equation 3 as two real and distinct roots, say m1 and m2. Then y equal to e power m1x and y2 equal to e power m2x are solutions of 2. So we can write a e power m1x and b e power m2x are solutions of 2, where a and b are arbitrary constants, or we can write in more general form, that is y equal to a e power m1x plus b e power m2x. And this is true when we have two real distinct roots, say m1 and m2. Now consider the case 2. Let the auxiliary equation 3 has two real roots but they are equal. Then let m2 equal to m1, then y equal to a e power m1x plus b e power m2x becomes a e power m1x plus b e power m1x. So that is equal to a plus b into e power mx. Where c is the single arbitrary constant equal to a plus b. So we have m1 and m2 are equal roots, then we have the solution in the form of equation 4. Thus the number of constant is reduced to 1, which is 1 short to the order of the differential equation 2, and therefore 4 chooses to represent the general solution. Hence we proceed like this way, that is, let us put m2 equal to m1 plus epsilon and allow epsilon to tend to 0, then y equal to a e power m1x plus b e power m1 plus epsilon into x. So now we take the common term outside, so we have e power m1x into a plus b e power epsilon x. Now we can represent this b e power epsilon x in terms of the series expansion, exponential series expansion, we have 1 plus epsilon x plus epsilon square x squared by 2 plus etc. So we have this equation. Now when epsilon tends to 0, the other terms tends to 0, so we have a plus b into epsilon into bx. Now we can choose b sufficiently big so that to make epsilon belongs to b, finite as epsilon tends to 0, and let a large with the opposite sign to b so that a plus b is finite. If a plus b equal to c and b equal to d, then the solution corresponding to real roots are e power m1 of x into c plus dx. Now we consider case 3. Let the auxiliary equation 3 has imaginary roots, that is, it has no real root. Then let that root be alpha plus I beta and alpha minus I beta. Since the complex roots occur in conjugate pairs, so we have m1 equal to alpha plus I beta is one root, means then we have m2 equal to alpha minus I beta. The solution is in the form of a e power m1 of x plus b e power m2 of x. Now substitute the value of m1 and m2 here. So we have this equation. So yeah, when we take e power alpha x outside, we have a e power I beta x plus b e power minus I beta x. Now we can write this in the equation, that is e power theta equal to cos theta plus I sin theta. So by using that concept here, you have this equation. So that is our Euler's formula. Now we have e power alpha x into c cos beta x plus d sin beta x, where c and d are arbitrary functions, arbitrary constants, and this also can be written as y equal to a e power alpha x into cos beta x plus b, where a and b are arbitrary constants. Now consider the examples. In the first example, we have the auxiliary equation as m square minus 5m plus 4 equal to 0. So by solving this equation, you have m equal to 1 and 4. So we have the solution. Similarly, when we consider the second equation, here m square plus 2m plus 1 equal to 0 is the auxiliary equation. So we have m equal to minus 1 twice. Now we consider the next result, that is, these results can be extended to the case of linear differential equations of higher order with constant coefficients. In the last section we have seen up to the second order. Now we are going to see the higher order with the constant coefficient. So the corresponding equation will be represented by the equation 1. Now here also we introduce the differential operator d by dx. So we have the equation. Now if we take that outside of y, then we have pi of d of y equal to 0. So we have y equal to a e power m1 x. So therefore the auxiliary equation is pi of m equal to 0. If the two roots of the equation are real and different, then this will be valid. So y equal to c1 e power m1x plus c2 e power m2x plus etc. cn e power mn x. Suppose if we consider case 2, then the roots are real equal roots, then we have m1 equal to m2, and the general solution of the equation 1 is y equal to c1 plus c2 of x, and so we have the solution y equal to c1 plus c2 of x into e power m1 of x plus e power m2 of x plus etc. alpha comma beta. Suppose if we consider the case 2, Then the auxiliary equation is corresponding to that, and we have finally m1 equal to m2. So the general solution becomes c1 plus c2 x e power m1 x plus c3 e power m2 of x plus etc. cn e power mn x. Suppose if the auxiliary equation has two real pairs of equal roots, say m1 and m2, then the general solution of the equation becomes y equal to c1 plus c2 of x into e power m1 of x plus c3 c4 x e power mx and so on. Suppose that if the auxiliary equation has all roots equal to m, then the general solution is in the form. Now consider the case 3. Here the roots of the equation are imaginary. Then it will occur in pairs. So we assume that if alpha plus I beta is one of the roots, then alpha minus I beta is also another root. So we have y equal to e power alpha x into c1 cos beta x plus c2 sin beta x plus c3 e power m3 of x plus etc. cn e power mn into n power x. If there are two pairs of imaginary roots, then the general solution is in the form. If pi of m equal to 0 has two real pairs of imaginary roots, say alpha plus or minus I beta, then the general solution is in this form. Now we will see one example related to this. So we have d square y by dx square, d cube y by dx cube plus 2 into d square y by dx square minus dy by dx minus 2y equal to 0. So in this given equation, we can see that the coefficient of the derivatives are all constant. So this is under the type of linear differential equations with constant coefficients. So we have the auxiliary equation, which is d cube minus plus 2d square minus d minus 2y equal to 0. Suppose if we consider the second equation, then d power 4 y by dx power 4 minus y equal to 0, then the equation can be written as d square minus 1 of y equal to 0. So we have the roots as 1 comma minus 1 comma plus or minus I. Hence the general solution of the equation 1 can be written as a e power x plus b e power minus x plus c cos x plus d sin x. Now consider the example 3. Solve d cube y by dx cube minus 3 into dy by dx plus 2y equal to 0. So by using the auxiliary equation, we find that m value, that is 1 comma 1 comma 1 comma minus 2. Then the general solution will be this one. So similarly, if you use this example, here the auxiliary equation is m cube minus 3m square plus 3m plus minus 2 equal to minus 1 equal to 0. So we have m minus 1 the whole square equal to 0. That is the general solution is y equal to a plus b x square into e power x. Similarly, we see the last example. So here the auxiliary equation is m power 4 plus 8m square plus 16 equal to 0, and so we have m square plus 4 of the whole square equal to 0. Hence the roots are plus or minus 2y comma plus or minus 2y. Hence the general solution is a plus bx plus cos 2x plus b plus c plus dx plus sin 2x. Thank you all. Hence, in this video, we learn about the linear differential equations with the constant coefficients. That is, we have learnt about the finding the solution of the linear differential equations with the constant coefficients.